Right now, at this very second, there is a spacecraft drifting through the dark, cold emptiness of interstellar space. It has been traveling for over 46 years. 46 years. And it has only made it to the very edge of our solar system. Not another star, not another galaxy. Just the edge of our own backyard. And here is the terrifying part. If we pointed that same spacecraft at the nearest star beyond our sun, it would take 73,000 years to get there. 73,000 years. That is longer than all of recorded human history, multiplied many times over. So the question is not whether we want to explore the stars. The question is, how on Earth, or rather how beyond Earth, do we actually get there? Stay with me tonight, because what I am about to show you will completely change how you think about space travel, rockets, and the future of humanity. Welcome. If you are watching this late at night, headphones in, lights off, wondering what is actually out there beyond the sky, then you are exactly the kind of person I made this video for. Please do me a favor, hit that like button and subscribe for more breakdowns. And comment, what do you think about future technology-based interstellar travel? Because tonight we are not doing a surface-level overview. We are going deep, really deep. We are talking about the most ambitious, the most mind-bending, the most genuinely revolutionary ideas that human engineers and physicists have ever dreamed up. Ideas that challenge the very laws of physics. Ideas that, if they work, would make humanity a multi-stellar species within the next 100 years. But before we get to the wild stuff, before we talk about warp drives and laser propulsion and spacecraft that surf on light itself, we have to understand something fundamental. We have to understand why the problem of space travel is so incredibly, brutally, almost unfairly hard. So let me paint you a picture. Imagine you are standing at the edge of a cliff, and below you is an ocean. And that ocean is not water. It is gravity, Earth's gravity. And to get a single object off the ground and into orbit, you have to fight that ocean. You have to push up against it so hard, so powerfully, that you overcome its pull entirely. And to do that, with the technology we have right now, you essentially have to strap yourself to a controlled explosion and ride it upward at thousands of miles per hour. That is what a rocket is. A controlled explosion. A beautiful, terrifying, awe-inspiring controlled explosion. And chemical rockets, the kind that have been launching humans into space since the 1960s, they work. Nobody is arguing they do not work. We used them to get to the moon. We used them to send probes to Jupiter, to Saturn, to the edges of the solar system. They are incredible machines built by incredible people. But here's the dirty secret that nobody really tells you in school. Chemical rockets are, in the grand scheme of cosmic travel, almost comically bad at what we need them to do for deep space. Here is why. To go somewhere far away, you need to go fast. And to go fast in space, you need to push your spacecraft. And to push your spacecraft, you need fuel. But here is the nightmare. Fuel has mass. And mass requires more fuel to push. And more fuel means more mass. And more mass means even more fuel. It is a vicious, self-defeating cycle that engineers call the Tsiolkovsky rocket equation. And it is one of the most humbling equations in all of science. Named after Konstantin Tsiolkovsky, a Russian scientist who figured this out in the late 1800s, the rocket equation essentially tells you how much fuel you need to achieve a given change in velocity. And the relationship is not linear, it is exponential, which means the faster you want to go, the amount of fuel you need does not just double or triple, it explodes. Think about it this way. The Saturn V rocket that sent Apollo astronauts to the moon weighed about 6 million pounds at launch. Do you know how much of that was fuel? About 85%. 85% of everything on that launch pad was just fuel. Fuel to burn, to push the fuel that pushes the fuel. And the moon is just 1 light second away from Earth, 1 single light second. Proxima Centauri, the nearest star beyond our Sun, is 4.2 light-years away. That is about 25 trillion miles. To put that in perspective, if the distance from Earth to the Moon were 1 inch, then the distance to Proxima Centauri would be about 4 miles. With chemical rockets at their current top speeds, a journey to Proxima Centauri would take roughly 70 to 100,000 years. We would send a spacecraft, and not just us, but every human civilization that ever existed. Every empire, every culture, every language that was ever spoken on this planet would have risen and fallen many times over before that spacecraft arrived. So yeah, chemical rockets are not going to cut it for interstellar travel. But here is the good news. And this is why I actually find this topic so thrilling to think about. We are not stuck. We are not at the end of the road. In fact, in a lot of ways, we are just at the beginning. And the ideas that scientists and engineers are working on right now, some in labs, some on paper, some already being tested in orbit, they are genuinely extraordinary. So let us start from the beginning. Let us build up your understanding of how propulsion actually works, why some methods are better than others, and then, step by step, we are going to climb the ladder from the rockets of the 1960s all the way up to concepts that sound like pure science fiction but are grounded in real, peer-reviewed physics. Buckle up. Section 3, Chemical Rockets, the Foundation. All right. Chapter 1, Chemical Rockets. The Old Faithful. To understand everything that comes after, you first need to understand how rockets actually work. Because the principle is deceptively simple, and yet the engineering involved is among the most complex humanity has ever attempted. Here is the core idea. Newton's third law. For every action, there is an equal and opposite reaction. If you throw something backward, you move forward. That is it. That is the fundamental principle behind all of rocket science. In a chemical rocket, you take two propellants, usually a fuel and an oxidizer, and you combust them together in a combustion chamber. The burning produces hot gas. That hot gas expands rapidly. You direct it out of a nozzle at the back of the rocket. Gas goes backward, rocket goes forward. Newton's law in action. Simple in principle, insanely complex in execution. Let us talk about specific impulse for a second, because this is one of the key metrics for understanding how good a propulsion system is. Specific impulse is basically a measure of efficiency. It tells you how much thrust you get for a given amount of propellant mass. The higher the specific impulse, the more efficient the engine, and the less fuel you need to carry. Chemical rockets have a specific impulse of somewhere between 300 and 450 seconds, depending on the propellants used. The best chemical propellant combination ever widely used is liquid hydrogen and liquid oxygen. This is what the space shuttle's main engines burned. It produces a specific impulse of about 450 seconds. Now that sounds decent, until you start comparing it to some of the other propulsion systems we are going to talk about later, where specific impulse values can reach into the tens of thousands, or even the millions of seconds. So why are chemical rockets still dominant if they are so limited? Because of one thing that no other current technology can match: thrust. Chemical rockets produce enormous thrust. The Saturn V, at liftoff, generated about 7.6 million pounds of thrust. That is enough force to lift about 35,000 cars simultaneously. That is what you need to get off the ground. That is what you need to fight Earth's gravity and punch through the atmosphere. The problem is, that massive thrust comes at the cost of fuel. And as we already discussed, fuel is heavy, and heavy is the enemy of everything in space travel. Now, within the world of chemical rockets, there has been constant, impressive innovation over the decades. Let us talk about SpaceX for a moment. Because what Elon Musk's company has done with rocket technology in the last 2 decades is genuinely remarkable. The development of reusable rockets, the Falcon 9 in particular, changed the economics of space launch in a way that almost nobody predicted. Before the Falcon 9, launching a kilogram of payload to low Earth orbit cost somewhere around $10,000 to $20,000. SpaceX brought that down to around $2,000 to $3,000 per kilogram, and they are actively working on reducing it further. The Starship program, SpaceX's next-generation fully reusable super heavy rocket, aims to reduce launch costs even further, potentially to a few $100s per kilogram in the long run. That is transformational. That makes the economics of sending things to space look completely different. And then there is the Raptor engine, which is the engine that powers Starship. The Raptor is a methane-fueled engine, and it is, by several measures, the most advanced chemical rocket engine ever built. It uses a full-flow staged combustion cycle, which is one of the most efficient and powerful engine cycles possible. It achieves chamber pressures that are the highest ever recorded in a production rocket engine. SpaceX has managed to make it at a scale and at a cost that was previously thought impossible. But even with all of this innovation, even with reusability and the Raptor engine and everything else, chemical rockets are still fundamentally limited by the chemistry. You can only get so much energy out of burning chemical propellants. The physics puts a ceiling on it, and that ceiling is nowhere near high enough for the journeys we want to take. Now let me introduce a concept that is going to come up again and again as we go through this video. Delta-V. Delta-V, written as a triangle-V in physics textbooks, simply means change in velocity. It is the total velocity change your spacecraft can achieve using its propellant. Every mission in space can be described in terms of how much delta-V it requires. Getting from Earth's surface to low Earth orbit requires about 9.4 kilometers per second of delta-V. Getting from low Earth orbit to the Moon requires about 3 more kilometers per second. Getting to Mars takes about 5 kilometers per second from low Earth orbit. Chemical rockets can deliver a finite amount of delta-V based on how much propellant they carry. And the rocket equation, which we mentioned earlier, means that to double your delta-V, you do not just double your fuel, you have to exponentially increase it. This is the fundamental brick wall that all of space exploration runs into when we start thinking about going farther than Mars. And it is why every other propulsion concept on this list is so exciting. Each one represents a different approach to breaking through that wall. Let us also briefly acknowledge the other main distinction in propulsion technology: the difference between propulsion systems that carry their own propellant and those that do not. Chemical rockets carry all their propellant with them. Ion thrusters carry their own propellant too, but use it far more efficiently. Solar sails carry no propellant at all. Laser propulsion systems carry no propellant either. This distinction between what you carry and what you use from the environment is going to become really important as we move forward. All right, so we understand chemical rockets. Powerful, reliable, limited. The workhorse of the space age, but not the vehicle of the interstellar age. Let us talk about what comes next. Section 4, Electric and Ion Propulsion, the Marathon Runners. Chapter 2, Ion Thrusters and Electric Propulsion. This is where things start to get really interesting. If chemical rockets are the sprinters of space propulsion, needing huge bursts of power to get off the starting line, then ion thrusters are the marathon runners. Slow to start, relatively low force but unbelievably efficient over long distances. Here's how an ion thruster works. You start with a propellant, not a chemical fuel like hydrogen or kerosene, usually something like xenon gas. Xenon is used because it is a noble gas, meaning it does not react with anything, and it is heavy enough that when you accelerate its atoms, they provide decent momentum. You take that xenon and you feed it into an ionization chamber. In there, electrons are stripped away from the xenon atoms using various methods. This turns the neutral xenon atoms into positively charged ions, hence the name ion thruster. Now you have these positively charged xenon ions. You then apply a powerful electric field across a pair of grids, one positively charged, one negatively charged. The positive ions are repelled by the positive grid and attracted to the negative grid. They accelerate through the gap between the grids and shoot out the back of the thruster at extremely high speeds. Speeds of around 30 to 90 kilometers per second, depending on the design. Compare that to chemical rocket exhaust, which exits at roughly 3 to 4 kilometers per second, so the exhaust is going much faster. And because of Newton's third law, faster exhaust means you need less of it to achieve the same momentum change. That is efficiency. That is what high specific impulse means in practice. Ion thrusters can achieve specific impulse values anywhere from 1,500 to 10,000 seconds, depending on the design. Compare that to the 450 seconds of the best chemical rockets. You are looking at a 3 to 20 times improvement in fuel efficiency. That means an ion thruster can do the same amount of velocity change with a fraction of the propellant, which means you can carry more payload, or you can travel farther on the same amount of propellant, or some combination of both. Sounds amazing, right? So why are we not using ion thrusters to send people to Mars right now? Because of thrust. Ion thrusters have incredibly low thrust. While a chemical rocket engine might generate thousands of pounds of thrust, a typical ion thruster generates thrust measured in millinewtons. A millinewton. That is roughly the force of a few postage stamps resting on your palm. To put that in perspective, some ion thrusters generate about 90 millinewtons of thrust. The weight of a single chocolate bar resting on your hand pushes down on your palm with more force than that. That sounds ridiculous. And in the context of getting off the ground, it absolutely is. You could not launch a spacecraft to orbit with an ion thruster. You would be there for centuries. But in space, where there is no air resistance and no gravity to fight, that gentle, constant, persistent push accumulates over time. And given weeks, months, or years of continuous operation, an ion thruster can build up delta V that a chemical rocket could never match without impossibly large amounts of fuel. This is exactly what has already been demonstrated in real missions. Let us talk about Dawn. Dawn was a NASA spacecraft launched in 2007. Its mission was to orbit 2 different bodies in the asteroid belt, Vesta and Ceres, something no spacecraft had ever done before. Visiting 2 separate destinations in a single mission sounds almost routine, but in terms of propulsion, it is extraordinarily demanding. You need enormous delta V to change orbits between 2 different targets. Dawn accomplished this using an ion propulsion system. Its 3 ion thrusters used xenon propellant and operated for years during the mission. Over the course of the entire mission, Dawn accumulated more than 11 kilometers per second of delta V from its ion thrusters. A chemical propulsion system capable of matching that performance would have been impossibly massive. And then there is Hayabusa. The Japanese spacecraft Hayabusa and its successor Hayabusa 2 used ion propulsion to travel to asteroids, collect samples from their surfaces, and return those samples to Earth. The round trip required precisely timed, long-duration ion thruster burns that would have been impossible with chemical propulsion at any reasonable spacecraft mass. And the European Space Agency's Smart 1 spacecraft used an ion thruster to spiral gradually from Earth orbit all the way to the Moon, demonstrating that electric propulsion could work for missions much closer to home, not just for deep space. So ion thrusters work. They are real, they are flying, they are getting better every year. Now let us talk about where this technology is heading, because the current generation of ion thrusters are just the beginning. One of the most exciting developments in electric propulsion is something called Hall effect thrusters. These are a variation on the ion thruster concept, but they use a magnetic field to trap electrons and ionize the propellant more efficiently. Hall thrusters have become the preferred choice for many satellite manufacturers because they offer a good balance of efficiency, thrust, and durability. SpaceX's Starlink satellites use Hall effect thrusters for station keeping, which is the process of adjusting their orbit to maintain their position. SpaceX is manufacturing Hall thrusters at a scale that was never before imagined in the space industry, which is driving down costs dramatically. There is also a newer concept called a gridded ion thruster, which is what NASA uses for its deep space missions, and these continue to improve in efficiency and specific impulse with each new generation. But even more exciting is the concept of solar electric propulsion, or SEP. The idea is straightforward. You use solar panels to generate electrical power, and you use that power to run electric thrusters. No batteries, no nuclear reactors, just sunlight converted to electricity to drive your ion engines. NASA's Dawn spacecraft used this approach, and NASA's Gateway program, which is the planned space station that will orbit the moon as a staging post for lunar surface operations and eventually for missions to Mars, will use solar electric propulsion for its power and propulsion elements. The Lunar Gateway's PPE, which stands for Power and Propulsion Element, will use an advanced solar electric propulsion system capable of generating about 60 kilowatts of electrical power. That is enough to power a very capable ion thruster system for long-duration maneuvering in the lunar vicinity. And looking further ahead, there are proposals for solar electric propulsion systems that could take cargo to Mars. Not quickly, not in the way a crewed mission would need to get there, but cargo missions, resupply missions, pre-positioning supplies and equipment before humans arrive. These are exactly the kind of missions where the high efficiency of ion propulsion outweighs the disadvantage of low thrust and long travel times. Now let us push the concept of electric propulsion a step further. What if instead of xenon, you use something else as your propellant? Something cheaper? Something you could find in space without having to bring it from Earth? This brings us to the concept of in situ resource utilization, or ISRU, applied to propulsion. The idea is to use materials found in space as propellant. Water ice is particularly attractive because it can be split into hydrogen and oxygen, which are excellent chemical rocket propellants. But even for electric propulsion, there are ideas about using regolith, which is the powdery surface material found on the Moon and Mars and asteroids, as a propellant. If you can ionize and accelerate it, it could work. There is also a technology called an electrodaedalus plasma thruster, which does not have grids or electrodes, meaning there is no part that physically contacts the superheated plasma. This is significant because the grids and electrodes in traditional ion thrusters wear out over time due to erosion by the high-energy plasma. An electrodeless design could potentially last much longer. Another fascinating electric propulsion concept is the field reverse configuration thruster and the magnetoplasma dynamic thruster. These are high-powered devices that can generate much higher thrust than traditional ion thrusters while still maintaining excellent efficiency. A magnetoplasma dynamic thruster could theoretically produce enough thrust to actually be useful for crewed missions, not just unmanned probes. The challenge is that they require enormous amounts of electrical power, on the order of hundreds of kilowatts to megawatts, which means you need a very powerful power source on your spacecraft. That power source is almost certainly going to be nuclear, which brings us to a topic we will explore in depth later in this video. But first, let me mention one more type of electric propulsion that is getting a lot of attention lately. Electrospray thrusters, also called colloid thrusters. These are tiny microscale thrusters that use electric fields to accelerate droplets of ionic liquid. They are incredibly small, incredibly efficient, and ideal for very small spacecraft. CubeSats, which are miniature satellites roughly the size of a shoebox, can use electrospray thrusters to maneuver and deorbit themselves in a controlled way. As the space industry continues to shrink and democratize, with hundreds of small satellites being launched every year, these tiny but efficient thrusters are becoming increasingly important. Alright, so we have chemical rockets, brute force but limited, ion thrusters, efficient but slow. Let us now look at something completely different. Let us look at a concept so elegant, so audacious, so literally otherworldly, that it sounds like something from a Jules Verne novel. Let us talk about the space elevator. Section 5. The space elevator, reaching for the sky. Chapter 3. The space elevator. Close your eyes for a second and imagine this. A cable stretching from the surface of the Earth all the way up into space, anchored at the bottom somewhere near the equator, and anchored at the top by a massive counterweight in geostationary orbit. And along this cable, climber vehicles travel up and down, carrying cargo and eventually people into space without any rockets, without any explosive fuel, without any of the violence and expense of a traditional launch. That is the space elevator concept. And it is not science fiction. It is a serious engineering proposal that some of the smartest people on the planet are working to make real. The basic physics of a space elevator works like this. Geostationary orbit is the altitude at which a satellite orbits the Earth at exactly the same rate as the Earth rotates. This orbit sits at about 35,786 kilometers above the equator. A satellite at this altitude stays fixed over one point on the Earth's surface, which is why geostationary satellites are used for communications and weather observation. If you put a massive counterweight above geostationary orbit, connected to a point on the equator below it by a cable, the outward pull of the counterweight from centrifugal force would balance the downward pull of gravity on the cable below. The whole structure would remain taut and stable. You could then send climber vehicles up this cable to reach orbit without burning a drop of fuel, or almost none. The energy to climb the cable would come from electricity, which could come from solar panels, from ground-based power, or even from lasers beamed up from the Earth to power the climbers directly. The economics are potentially extraordinary. Getting a kilogram of payload to geostationary orbit using traditional rockets costs many thousands of dollars. A space elevator, once built, could potentially do it for hundreds of dollars per kilogram or even less. Now you might be thinking, okay, this sounds great. Why are we not building it already? And the answer comes down to one brutal, unavoidable constraint. The cable. The cable of a space elevator has to be in tension along its entire length. The upper part of the cable is being pulled outward by the centrifugal effect of the counterweight orbiting in space. The lower part is being pulled downward by gravity. The cable has to support all of that stress, all of that tension, while also being light enough that its own weight does not cause it to collapse. The ratio of a material's tensile strength to its density is called the specific strength. To build a space elevator cable that would work with Earth's gravity, you need a material with a specific strength of at least 63 megapascals per kilogram per cubic meter. Every material that exists in any quantity on Earth today falls far short of that requirement. Steel? Way too weak and too heavy. Kevlar? Better, but still not close. High-strength carbon fiber? Getting closer, but still not there. The only material currently known that might be strong enough is carbon nanotubes. Carbon nanotubes are cylinders of carbon atoms arranged in a hexagonal lattice similar to graphene. At the molecular scale, they are extraordinarily strong. Individual carbon nanotubes have demonstrated tensile strengths of roughly 63 to 100 gigapascals, which puts them right in the range needed for a space elevator cable. But here is the problem. We cannot currently manufacture carbon nanotubes at the required scale. We can make them in tiny quantities in laboratories. We can make carbon nanotube fibers that are useful for some engineering applications. But a space elevator cable would need to be tens of thousands of kilometers long, with consistent, defect-free strength throughout. Defects in carbon nanotube fibers dramatically reduce their macroscale strength, bringing it far below the theoretical values measured on individual nanotubes. Manufacturing carbon nanotubes in the quantity and quality needed for a space elevator cable is beyond our current technology, but it is not beyond our imagination. And research into carbon nanotube synthesis and processing is advancing every year. The most concrete proposal for a space elevator in recent years has come from a Japanese construction company called Obayashi Corporation. In 2012, Obayashi announced plans to build a space elevator by 2050. Their concept involves a cable made from carbon nanotubes, a 36,000-kilometer-long cable stretched from Earth to a geostationary station, with climber vehicles powered by linear motors and magnetic levitation. Now, Obayashi's 2050 target was always optimistic, and many engineers consider it unrealistic given where carbon nanotube technology currently stands. But the fact that a major construction company is taking it seriously enough to develop a detailed engineering concept tells you something about where the conversation has moved. There are also less ambitious versions of the space elevator concept that are closer to current technology. A lunar space elevator, for example, would be far easier to build. The Moon has much weaker gravity than Earth and no atmosphere, so the specific strength requirements for the cable are much lower. Materials like high-strength Xylon or Dyneema could potentially work for a lunar elevator. And a lunar elevator could greatly reduce the cost of transporting materials from the Moon's surface to lunar orbit, which is important if the Moon is ever going to serve as a source of resources for the rest of the solar system. There is also the concept of a skyhook, which is a shorter version of the space elevator concept. A skyhook is a rotating tether in orbit. As the lower end of the tether swings close to the atmosphere, a suborbital vehicle flying at high speed can grab on and be slung upward into a higher orbit. The skyhook concept does not require exotic materials because it does not need to reach all the way from the ground. It only needs to dip its lower end into the upper atmosphere briefly. This makes it much more achievable with current or near-future materials. The skyhook concept was seriously studied by NASA in the 90s and early 2000s. And a company called Tethers Unlimited has been developing tether technology for various space applications. But let us get back to the full space elevator concept because I want to make sure we appreciate what it would mean if this actually worked. Right now, Earth is essentially a closed system in terms of resources. Everything we build, everything we use, every product manufactured on this planet uses materials that came from the Earth. Mining, drilling, quarrying, farming, all of it comes from our planet. And our planet is finite. The minerals, the metals, the rare elements that our technology depends on, they are limited. And we are using them at an accelerating rate. Space, on the other hand, is almost unimaginably resource-rich. The asteroid belt alone contains enough iron and nickel to build structures with a total surface area many thousands of times greater than the Earth's. The gas giants have atmospheric reserves of helium-3, a potential fusion fuel that dwarf anything available on Earth. The ice on comets and in the outer solar system contains water in quantities that make Earth's oceans look modest. The problem is getting to all that stuff. And even if you can get to it, getting it back to Earth in any economically useful way requires being able to move things around cheaply. And that means getting out of Earth's gravity cheaply. A space elevator would change that equation fundamentally. If you can lift cargo to geostationary orbit for a few $100s per kilogram, then suddenly asteroid mining becomes economically viable. Orbital manufacturing becomes possible. Building large structures in space becomes feasible. The entire paradigm of the space economy changes. So while a space elevator might seem like a distant, uncertain dream, the potential payoff is so enormous that it absolutely justifies continued research and development. Even incremental progress toward the materials science needed for a full Earth space elevator could unlock other applications in the meantime. Now, let us move from the elegant simplicity of the space elevator to something that has been both the subject of serious scientific research and some pretty intense public debate. Let us talk about nuclear propulsion. Section 6. Nuclear propulsion. The power of the atom. Chapter 4. Nuclear propulsion. The word nuclear makes a lot of people uncomfortable. It has a complicated history, wrapped up with weapons, with Chernobyl, with Fukushima. But strip away all of that baggage, and what you are left with is simply this. Nuclear reactions release an enormous amount of energy compared to chemical reactions. And in propulsion, energy is everything. There are two main branches of nuclear propulsion that are seriously being discussed and developed for space applications: nuclear thermal propulsion and nuclear electric propulsion. Let us break both of them down. Nuclear thermal propulsion, or NTP, is conceptually pretty straightforward. Instead of burning chemical propellants to generate heat and expand gas through a nozzle, you use a nuclear reactor to heat a propellant, most likely liquid hydrogen, to extremely high temperatures. The hot hydrogen expands and shoots out the back of the engine, generating thrust. The advantage is significant. Because nuclear reactors can generate far more heat than any chemical combustion process, the hydrogen propellant can be heated to much higher temperatures than any combustion product. Higher temperature means the exhaust exits faster. Faster exhaust means higher specific impulse. Nuclear thermal engines can achieve specific impulse values of around 800 to 1,000 seconds, roughly double that of the best chemical engines. Double the specific impulse means you need roughly half as much propellant to do the same job, which means you can either carry more payload, or you can travel faster for the same payload mass, or you can accept a lighter overall spacecraft. For a mission to Mars, this is significant. With chemical propulsion, a crewed mission to Mars using current trajectory planning takes somewhere between 6 and 9 months one way. With nuclear thermal propulsion, that trip time could potentially be reduced to around 3 to 4 months. Cutting the trip time in half is not just a matter of comfort. It dramatically reduces the crew's exposure to deep space radiation, one of the most serious health hazards for long-duration space missions. Nuclear thermal propulsion is not a new concept. The United States actually built and tested nuclear thermal rocket engines in the 1960s and 70s, under programs called NERVA and ROVER. These tests demonstrated that nuclear thermal propulsion worked, that the engines could produce thrust, that these specific impulse advantages were real. The NERVA engine passed all of its design goals, and then the program was canceled, largely for political and budgetary reasons as the Apollo era wound down and public enthusiasm for ambitious space programs faded. Fast forward to today, and there is a genuine renaissance of interest in nuclear thermal propulsion. NASA and DARPA are jointly developing a nuclear thermal rocket engine called the Demonstration Rocket for Agile Cislunar Operations, or DRACO. The goal of the DRACO program is to develop and demonstrate an operational nuclear thermal rocket by the mid-2020s. The DRACO engine would use a high-assay, low-enriched uranium fuel, which is a type of nuclear fuel that is enriched to a higher degree than typical reactor fuel but not to the extreme levels used in nuclear weapons. This makes the fuel suitable for space applications while keeping it in a category that does not raise the same non-proliferation concerns as highly enriched uranium. If DRACO succeeds, it will be the first in-space demonstration of nuclear thermal propulsion. And it would open the door to using NTP for a wide range of missions, including crewed Mars missions, rapid transit around the cislunar environment, and eventually, potentially, even outer solar system missions. Now let us talk about nuclear electric propulsion, or NEP. This is the combination of two things we have already discussed: a nuclear power source and electric thrusters. The idea is to use a nuclear reactor to generate electrical power, and then use that power to run ion thrusters, or Hall effect thrusters, or other types of high-efficiency electric propulsion. The advantage of nuclear electric propulsion over solar electric propulsion is that it works anywhere. Solar panels produce less power the farther you get from the sun. By the time you reach Jupiter, you are receiving only about 4% of the sunlight that hits Earth. At Saturn, it is even less. This makes solar electric propulsion increasingly impractical for outer solar system missions. A nuclear reactor, on the other hand, produces the same amount of power regardless of where you are in the solar system. Whether you are at Mars or at Neptune, your reactor keeps humming along. Combine nuclear power with high-efficiency electric thrusters, and you have a propulsion system that is both efficient and capable of operating anywhere in the solar system. One key metric for nuclear electric propulsion systems is the power-to-mass ratio of the reactor. The more power you can generate per kilogram of reactor mass, the more attractive NEP becomes. Current nuclear reactor designs for space applications are relatively heavy compared to the power they produce, but this is an active area of research. NASA's KiloPower project developed a small nuclear fission reactor called CRUSTY, which stands for Kilowatt Reactor Using Stirling Technology. This is a small, compact fission reactor capable of producing 1 to 10 kilowatts of electrical power. It was tested successfully in ground-based demonstrations at the Nevada National Security Site. 1 to 10 kilowatts is modest, but it is enough to power a small outpost on the Moon or Mars, or to run a compact ion propulsion system on a small spacecraft. And importantly, it proves the concept. Larger, more powerful versions could follow. For truly high-power NEP systems that could drive fast crewed missions, you would need reactors in the range of hundreds of kilowatts to megawatts. These are much more challenging to develop, but not physically impossible. The Soviet Union actually operated nuclear reactors in space during the Cold War, under a program called RORSAT. These were radar reconnaissance satellites powered by nuclear reactors. Dozens of RORSAT satellites were launched, and they demonstrated that nuclear power in space was operationally feasible, though some of the early designs had issues with radioactive contamination when they re-entered the atmosphere. Now let me throw in a third nuclear propulsion concept that goes even further than NTP or NEP, something called nuclear pulse propulsion. Nuclear pulse propulsion is exactly what it sounds like. You detonate small nuclear bombs behind your spacecraft, and the shockwave pushes you forward, over and over again. This concept was studied in dead seriousness by the United States government in the late 1950s and 1960s under a program called Project Orion. The physicist Freeman Dyson was one of the key researchers. Their analysis showed that nuclear pulse propulsion was genuinely feasible and could deliver performance that dwarfs any other propulsion system. The specific impulse of a nuclear pulse drive could theoretically reach into the tens of thousands of seconds. For very large spacecraft, thrust could be enormous. The Orion concept called for a large pusher plate at the back of the spacecraft to absorb and transmit the force of each detonation. Shock absorbers would smooth out the impulse so that the crew inside did not experience the full violence of each nuclear detonation. Project Orion designs ranged from small vessels to absolutely enormous spacecraft. One proposed design was the size of a battleship, capable of carrying hundreds of crew members to Mars in just weeks, or to Saturn in a few years. Freeman Dyson himself believed that Orion-type spacecraft could make interstellar travel possible within the 21st century using existing technology. The concept was eventually abandoned, primarily due to the 1963 Partial Test Ban Treaty, which prohibited nuclear weapons testing in the atmosphere, in space, and underwater. Detonating nuclear bombs in space, even for propulsion purposes, fell under the treaty's prohibitions. But the physics remained sound. And there have been proposals for versions of nuclear pulse propulsion that use fusion microbursts instead of fission weapons, which might eventually sidestep some of the legal and political obstacles. The inertial confinement fusion rocket, sometimes called a mini magnetospheric plasma propulsion system or similar variants, explores these ideas. And there is another concept in this space, literally and figuratively, called the Z-pinch fusion rocket, which uses magnetic fields to compress plasma to the point of nuclear fusion. The pulses of fusion energy are then directed backward to provide thrust. This is still conceptual, but it is grounded in plasma physics research that is ongoing. Let me also mention a related idea called the nuclear photonic rocket. This is a concept where a nuclear reactor heats a material to such extreme temperatures that it glows brightly, and the radiation pressure of the light produced provides thrust. It is extraordinarily inefficient compared to other methods, essentially useless for near-term applications, but it illustrates how creative the ideas in this space have gotten. Alright, nuclear propulsion, two main branches. Nuclear thermal, doubling the efficiency of chemical rockets and potentially having trip times to Mars. Nuclear electric, combining reactor power with ion thrusters for high efficiency throughout the solar system. And nuclear pulse, the wild card, detonating nuclear bombs for raw performance that makes everything else look slow. Each of these is real science. Each of these has been seriously studied, and in the case of NTP, already demonstrated in ground tests. The barriers are not scientific impossibility. They are engineering challenges, funding constraints, and political considerations. Let us now move to something fundamentally different from everything we have discussed so far. Let us talk about propulsion systems that do not carry any propellant at all. Section 7. Propellanttless. Propulsion, sailing on light and riding magnetic fields. Chapter 5. Propellantless propulsion. This is where the ideas start to sound genuinely magical. Every propulsion system we have talked about so far carries some kind of propellant. Chemical rockets carry fuel and oxidizer. Ion thrusters carry xenon. Even nuclear thermal engines carry hydrogen propellant. The nuclear reaction just heats the hydrogen. You still need to bring the hydrogen with you. But what if you did not? What if you could push your spacecraft through space without carrying any reaction mass at all? This is not a new idea. Sailors figured out centuries ago how to harness the wind, an external force, to propel their ships across the ocean without any internal engine. The analogy for space is a solar sail, and it works on real, measurable physics. Here is the thing that surprises most people. Light has momentum. Photons, which are the particles that make up light, carry momentum even though they have no mass. This is a consequence of quantum mechanics and relativistic physics. When photons hit a surface and bounce off, they transfer some of that momentum to the surface. This is called radiation pressure. The radiation pressure from sunlight is incredibly small. At Earth's distance from the sun, it is about 9 micronewtons per square meter. That is 9 millionths of a newton per square meter of area facing the sun. If you tried to feel radiation pressure by holding your hand in sunlight, you would need instruments far more sensitive than anything biology provides. The force is simply too small to perceive. But in space, where there is no air resistance, even a tiny force, applied over a long enough time, adds up to meaningful velocity. The key insight of the solar sail is this. If you make a very large, very thin, very lightweight sail and deploy it in space, the radiation pressure of sunlight will push it. And unlike a rocket or ion thruster, you do not run out of propellant. As long as you have sunlight, you have thrust. The mathematics works out nicely. A solar sail with a surface area of 800 square meters, made from an aluminized polyester film just a few micrometers thick, weighing about 10 kilograms, would experience about 7.2 micronewtons of force from sunlight at Earth's distance from the sun. That sounds tiny. But that same sail could continuously accelerate a small spacecraft for years. Over the course of months, you could build up significant velocity. Solar sails have already been demonstrated in space. The Japanese space agency JAXA launched a spacecraft called Icaros, which stands for Interplanetary Kitecraft Accelerated by Radiation of the Sun, in 2010. Icaros deployed a 14-meter square sail in interplanetary space and successfully demonstrated solar sail propulsion. The spacecraft navigated past Venus and eventually entered a heliocentric orbit. NASA's NanoSail D tested solar sail deployment in 2010, and NASA's CubeSat mission called LightSail 2, developed by the Planetary Society, successfully demonstrated controlled solar sailing in Earth orbit in 2019, using its sail to raise its orbital altitude. These are small demonstrations, but they prove the principle. Where solar sailing gets really exciting is when you start thinking about much larger sails and missions that take advantage of the unique capabilities of the technology. One proposal involves sending solar sail spacecraft on trajectories that pass very close to the sun, called a perihelion pass or a sundiver maneuver. Close to the sun, radiation pressure is much stronger, varying as the inverse square of the distance. At a distance of 1/10 of an astronomical unit from the sun, radiation pressure is 100 times stronger than at Earth's distance. A solar sail doing a close solar pass could gain enormous velocity from this brief, intense radiation pressure boost, then be flung outward toward the outer solar system or beyond at high speed. Some calculations suggest that a solar sail doing an extremely close pass of the sun could achieve velocities of several hundred kilometers per second. To put that in perspective, the Voyager 1 spacecraft, the fastest human-made object ever, travels at about 17 kilometers per second. A solar sail using a perihelion pass could potentially travel 10 to 20 times faster than that. Now, there are enormous engineering challenges. Getting a solar sail that close to the sun while keeping it from burning up is extremely difficult. But the fundamental physics works. Looking even further ahead, solar sails point toward a concept that goes far beyond anything we can do with solar radiation alone. Laser sails, or light sails, powered not by sunlight, but by powerful lasers beamed from Earth, or from a platform in space. We will come back to this idea in much more detail when we talk about laser propulsion later in the video, because this is one of the most promising concepts for reaching another star within a human lifetime, and it deserves its own extended discussion. But first, let me tell you about another propellantless propulsion concept that is completely different from solar sailing. Let me tell you about tethers. Space tethers are long, conductive cables deployed from a spacecraft in orbit. When a conductive cable moves through a magnetic field, it generates an electric current. And when you run an electric current through a conductor in a magnetic field, you generate a force. If you deploy a long conductive tether from a spacecraft in low Earth orbit, the tether cuts through Earth's magnetic field lines as the spacecraft moves. This induces a current in the tether. You can then control the direction of that current to either slow down or speed up the spacecraft's orbit. This is the electrodynamic tether concept, and it is remarkable because it requires no propellant. The energy comes from Earth's magnetic field, not from any fuel you carry. In terms of gaining or losing orbital energy, the tether exchanges momentum with the Earth's magnetosphere. Electrodynamic tethers have been tested in space. NASA's Tethered Satellite System experiments in the 1990s demonstrated the basic physics, though they also encountered some practical difficulties. One of the tether cables broke unexpectedly due to a failure in the insulation, which led to a dramatic and spectacular result. The disconnected satellite at the end of the tether rapidly moved away at high speed, exactly as the tether mechanics predicted, just not in a controlled way. Despite this failure, the experiment provided enormous amounts of data and largely validated the theoretical predictions. More recently, there has been interest in using tethers as a deorbit system for defunct satellites. One of the major problems with space junk in low Earth orbit is that without active deorbit systems, satellites and rocket bodies remain in orbit for years or decades after they stop functioning. An electrodynamic tether could, in principle, be deployed from a dead satellite to slow it down and bring it back into the atmosphere to burn up, solving the space debris problem at low cost. Beyond deorbiting, electrodynamic tethers have been proposed for more ambitious applications. The momentum exchange tether concept uses a very long rotating tether in space to grab payloads in low Earth orbit and fling them to higher orbits or beyond. This is related to the rotating skyhook concept we mentioned earlier. The tether rotates in space, and when the lower end sweeps past a spacecraft at the right speed, they can mate, and the spacecraft is slung outward. The energy for this maneuver comes partly from the tether's rotation, which has been built up using electrodynamic effects over time. There are also proposals for tethers at other planets. A lunar gravity assist tether at the Moon could intercept incoming spacecraft and fling them toward deep space destinations. A similar tether at Mars could capture arriving spacecraft and provide orbital insertion without burning any propellant. Tether systems are still in early development, and most of the advanced concepts are still on paper. But they represent a genuinely promising approach toward reducing the propellant requirements of space travel, leveraging the electromagnetic environment of the solar system as a resource. Let me also touch on another propellantless concept that is gaining interest. The magnetic sail, or magsail.a magnetic sail, uses a large superconducting loop to generate a magnetic field that extends for hundreds of kilometers around the spacecraft. The solar wind, which is a stream of charged particles constantly flowing outward from the sun, interacts with this magnetic field. The pressure of the solar wind pushing against the magnetic bubble provides thrust, just like the solar wind pushing against a physical sail. The advantage of a magnetic sail over a physical solar sail is that it does not require a huge, fragile physical structure. A superconducting coil can be relatively compact, and the resulting magnetic field can extend over a much larger effective area than any physical sail could. And unlike a solar sail, which is only pushed by photons in the direction away from the sun, a magnetic sail can potentially be steered by adjusting the shape of the magnetic field to deflect the solar wind at different angles. The challenge with magnetic sails is producing and maintaining the superconducting current in the coil. Superconductors require low temperatures to maintain their superconducting state, and keeping a large loop of superconducting in deep space far from the sun, temperatures naturally drop low enough that many superconductors would work without active cooling. But in the inner solar system, where solar heating is more intense, the thermal engineering becomes challenging. There are proposals to use a new class of materials called high-temperature superconductors, which maintain their superconducting properties at much higher temperatures than traditional superconductors. If the advances in high-temperature superconductors continue as hoped, magnetic sails could become much more practical. The electrostatic sail, or e-sail, is a related concept developed by Pekka Junhunen of the Finnish. Instead of a magnetic field, the e-sail uses long, thin, electrically charged wires extending from the spacecraft. The positive charge on the wires repels the positively charged protons in the solar wind, creating an interaction that accelerates the spacecraft away from the sun. The e-sail has several potential advantages over physical solar sails. The wires are much lighter per unit effective area than a physical sail film. The effective interaction area can be adjusted by changing the wire voltage. And the wires are simpler to deploy and retract than a large sheet. Calculations suggest that an e-sail with 20-kilometer-long wires could potentially provide enough thrust to reach the outer solar system much faster than any conventional spacecraft. ESA has conducted ground-based testing of e-sail components, and there have been proposals for in-space demonstrations. But as of now, it has not yet been demonstrated in flight. All right? Propellantless propulsion, solar sails, laser sails, electrodynamic tethers, momentum exchange tethers, magnetic sails, e-sails. All of these represent ways to move through space by tapping into external forces and energy sources rather than carrying propellant. They are not the fastest propulsion concepts we have, but they are some of the most elegant. And for certain missions, certain trajectories, they could be transformative. Now let us step through the door into territory that is truly at the edge of physics. Let us talk about warp drives. Section 8. Warp drives. The physics of the impossible Chapter 6. Warp drives. Okay. I need to be honest with you here from the beginning. This section is going to be different from everything that came before it, because everything we have discussed so far is either currently operational, or a well-understood extension of existing technology, or at least firmly grounded in mainstream physics. Warp drives are different. Warp drives sit right at the boundary between serious theoretical physics and speculative science fiction. There are real physicists who work on this. There are real papers published in peer-reviewed journals about it. But there are also enormous fundamental obstacles that may or may not ever be overcome. I am going to give you the full picture, the exciting part, and the sobering part. Let us start with the basic idea. The speed of light, conventionally denoted by the letter c, is about 299,792 kilometers per second. That is roughly 300,000 kilometers every second. According to Einstein's special theory of relativity, nothing with mass can travel at or exceed the speed of light. As any object with mass accelerates toward the speed of light, it requires more and more energy to continue accelerating. The faster you go, the more energy you need. As you approach the speed of light, the energy required approaches infinity. So for any conventional spacecraft with mass, whether it uses chemical rockets or ion thrusters or nuclear propulsion, the speed of light is a hard limit. You can approach it asymptotically. You can never reach it. This has devastating implications for interstellar travel. Even if you could somehow travel at 90% of the speed of light, which would require unimaginable amounts of energy, a journey to Proxima Centauri would still take about 4 to 5 years. A journey to the center of the Milky Way, about 26,000 light-years, would take nearly 30,000 years. The galaxy is simply too big. The stars are simply too far. Even at the speed of light, the universe is effectively unreachable in human timescales. Unless you find a way to cheat. In 1994, a Mexican physicist named Miguel Alcubierre published a paper in the journal Classical and Quantum Gravity titled "The Warp Drive: Hyperfast Travel Within General Relativity." And this paper got a lot of people very excited. Here is Alcubierre's idea. Einstein's general theory of relativity, which is our best description of gravity and spacetime, says that space itself can expand and contract. And, crucially, there is no known limit on the speed at which space itself can expand. We actually know from cosmology that the universe is expanding, and distant parts of the universe are moving away from us faster than the speed of light. That does not violate relativity because it is space itself expanding, not objects moving through space. Alcubierre asked, could you create a localized distortion of space-time that would effectively move a spacecraft from one place to another faster than light, without the spacecraft itself ever locally exceeding the speed of light? His proposed solution is mathematically elegant. You compress space-time in front of the spacecraft and expand space-time behind it. The spacecraft sits in a bubble of flat space-time, a region where normal physics applies. The space-time distortion carries the bubble and everything inside it to the destination. From inside the bubble, the passengers feel no force, no acceleration. They are sitting in flat space-time. But from an outside observer's point of view, the bubble and everything inside it move faster than light. This is the Alcubierre drive, or, as it became known in popular culture, the warp drive. And the mathematics of general relativity does actually allow for this solution. It is a valid solution to Einstein's field equations. This is the part that is genuinely exciting and why physicists take it seriously. But then come the problems. And they are significant. Problem 1. The energy required. Early analysis of the Alcubierre metric suggested that the energy required to create the warp bubble was on the order of 10 to the 45th joules, which is roughly the energy equivalent of turning an entire Jupiter-mass planet into pure energy. Using E equals mc squared, that is not a practical constraint. That is universe-scale obstacle. More recent work, by Harold White at NASA and others, suggested that by modifying the shape and configuration of the warp bubble, the energy requirements could potentially be dramatically reduced. White proposed a design that, under certain assumptions, could reduce the energy requirement to something merely astronomical rather than cosmologically impossible, on the order of about 700 kilograms of mass energy, using equals mc squared to convert mass to energy. Even that reduced estimate is far beyond any foreseeable technology. But the direction of the research was encouraging, suggesting that clever engineering might continue to reduce the energy requirement. Problem 2. Exotic matter. The space-time distortion required for the Alcubierre drive requires what physicists call exotic matter. Note exotic in the colloquial sense of unusual. Exotic in the imprecise technical sense. Matter with negative energy density. Normal matter has positive energy density. A rock, a gas cloud, a star, all have positive energy. Negative energy density matter is matter that has energy less than zero, which sounds physically absurd. And it kind of is. Normal matter as we encounter it everywhere in the universe does not have negative energy density. But, intriguingly, quantum mechanics does allow for very small amounts of negative energy density to exist in certain carefully arranged conditions. This is related to phenomena like the Casimir effect, where two very closely spaced metal plates in a vacuum experience an attractive force because of quantum vacuum fluctuations between them. The problem is the scale. The negative energy density effects that quantum mechanics allows are incredibility on scales and in quantities that are many orders of magnitude below what the Alcubierre drive would require. it is not quite accurate to say that exotic matter is known to be impossible. It is more accurate to say that we know of no way to produce it in the quantities needed, and some researchers believe that fundamental physical constraints may prevent us from ever doing so. Problem 3. Causal issues. This one is subtle but potentially fatal. Some analyses of the Alcubierre drive suggest that creating the warp bubble in the first place might require information or signals to travel to the edge of the bubble at superluminal speeds. In other words, you might need faster-than-light signaling to create a faster-than-light drive, which makes the whole thing bootstrapped in a way that seems logically problematic. There are also deep questions about the relationship between warp drives and causality, the principle that causes precede effects. If you can effectively travel faster than light, you might also be able to travel backward in time, in a certain sense. And that opens up all the paradoxes associated with time travel, which suggests that physics might have some deep protection mechanism that prevents this. Some physicists invoke something called dechronology protection conjecture, proposed by Stephen Hawking, which holds that the laws of physics conspire to prevent travel backward in time, and therefore might also prevent anything that would allow it as a side effect. Problem 4. Control and stability. Even if you could create the warp bubble, controlling itis, another challenge entirely. The interior of the bubble is causally disconnected from the edge. That means someone inside cannot send signals to the outer edgeito, modify, or deactivate the bubble. You cannot steer it from inside. This is a fundamental issue that has not been resolved. So where does all of this leave us? Honestly, in a state of genuine uncertainty. The Alcubierre drive is real mathematics, grounded in real general relativity. But the practical obstacles are formidable and possibly insurmountable. The energy requirements, even in optimistic estimates, are far beyond anything human civilization could realistically produce for the foreseeable future. The need for exotic matter is a fundamental physical challenge, not just an engineering problem. And the causal issues may indicate something deeper about whether this kind of travel is consistent with physical law. Harold Dwight at NASA's Johnson Space Center did Runa research programs specifically aimed at looking for evidence of space-time warping at small scales, using an interferometer designed to detect tiny changes in space-time geometry. The goal was not to build a warp drive, but to detect any measurable warping effect from a particular arrangement of electric charges and magnetic fields. As of the last information I have, no positive results have been published, and in 2021, a paper by Eric Lentz proposed a new type of warp solution that, unlike Alcubierre's, does not require exotic matter with negative energy. Lentz's solution uses a different mathematical formulation of the space-time geometry, involving soliton-like structures. However, the energy requirements for Lentz's solution are still colossal, on the order of the mass energy of Jupiter, far beyond anything practical. The takeaway on warp drives is this: they represent a genuinely interesting area of theoretical physics. They are not entirely fictional, but they are also note engineering problems that are close to being solved. They are conceptual puzzles whose resolution depends on deepening our understanding of fundamental physics in ways that are currently beyond our reach. If we ever do develop warp drives, it will likely require breakthroughs in our understanding of quantum gravity, the relationship between quantum mechanics and general relativity that are currently not fully understood. And yet, I would not count it out entirely. 150 years ago, quantum mechanics did not exist. Relativity did not exist. The idea that you could create a chain reaction in atomic nuclei to release enormous energy was unknown. Physics has surprised us before, in ways that opened up technologies that would have seemed magical to earlier generations. So, warp drives. Real physics, real mathematics, real obstacles, uncertain future. Not going to help us get to Alpha Centauri next century. But maybe not forever beyond reach either. Let us come back to Earth a bit, or at least come back to technologies that are closer to demonstrable, and talk about one of the most genuinely exciting and promising near-term concepts for interstellar travel. Let us talk about laser propulsion. Section 9, Laser, and BEAMPROPULSION, writing a river OFLIGHT Chapter 7, Laser Propulsion and Beam Sailing. This, I would argue, is the most exciting near-term concept for interstellar travel that actually has a plausible path to implementation. Let me set the scene. It is the year 2017. A group of scientists and engineers, backed by the boldest private space initiative since the moon race, announced a project with a staggering goal. Send a spacecraft to another star within a generation, not within centuries, within the lifetime of people alive today. The project is called Breakthrough Starshot, and it is funded in part by Russian internet entrepreneur Yuri Milner, who has committed $100 million to the research phase. Stephen Hawking was one of the public faces of the project before his death in 2018. The concept is breathtakingly ambitious and, unlike warp drives, is grounded in technology that either already exists or is a credible extension of existing capabilities. Here is how it works. You build a fleet of tiny spacecraft. Not the kind of spacecraft we normally think of. These are wafer-thin chips, roughly the size of a postage stamp, weighing about a gram. Each one contains a camera, a communication system, navigation sensors, and basis electronics. They are called star chips. Each star chip deploys a tiny sail. Not a cloth sail, not a plastic film, but an ultra-thin reflective sail made from a highly reflective metamaterial, possibly just a few atoms thick. The sail might be a few meters across, but the total mass of the sail plus the chip is still only a few grams. Now comes the power source. Not on the spacecraft out on Earth, or in orbit. You build a laser array. A huge one. An array of individual lasers, each individually steerable, all focused together on a single point. The total output of this laser array would be approximately 100 gigawatts. That is about equal to the entire power output of the United States electrical grid. You fire this laser array at the tiny sail spacecraft. The radiation pressure of 100 gigawatts of laser light, focused on a sail only a few grams in mass, would accelerate the spacecraft at thousands of g-forces. In a matter of minutes, the spacecraft would be moving at a significant fraction of the speed of light. The target speed is 20% of the speed of light. 0.2 circa. At 20% of the speed of light, the journey to Proxima Centauri, 4.2 light-years away, would take about 20 years. 20 years. Not 70,000 years. Not even 100 years. 20 years, you would launch the spacecraft. Wait 20 years for it to arrive. Then wait another 4 years for its signal, traveling at light speed, to return to Earth. And around 24 years from launch, you would start receiving images and data from another stellar system. That is the Breakthrough Starshot vision. And it is not based on any exotic physics, no warp drives, no exotic matter. Just lasers, tiny spacecraft, and the physics of radiation pressure. Now let me be absolutely honest about the challenges, because there are many. Challenge 1. The laser array. 100 gigawatts of laser power is an enormous amount of energy to concentrate into a single beam. The laser array itself would be massive. Current high-power laser technology, as of the early 2020s, can produce megawatts. Getting to gigawatts, let alone 100 gigawatts, requires scaling existing technology by several orders of magnitude. The individual lasers in the array would need to be precisely phase coherent, meaning their light waves would all need to be synchronized and in phase with each other to produce a focused, coherent beam rather than an incoherent blur. Maintaining phase coherence across an array of this scale, over distances of thousands of kilometers, with their required precision, is an engineering challenge of staggering difficulty. The array itself would need to be enormous. Depending on the wavelength of light used and the distance at which the beam needs to be focused, the aperture of the array might need to be a kilometer or more, in diameter. Challenge 2. The sail. The sail needs to be highly reflective. Any laser light absorbed by the sail rather than reflected would heat sail, potentially to the point of destruction. If you're shining 100 gigawatts at a gram scale sail, you need reflectivity approaching 100%, and even a fraction of a percent of absorption could be catastrophic. The sail also needs to be mechanically stable during the acceleration phase. The laser pressure is not perfectly uniform across the sail, and any asymmetry could cause the sail to tumble or the beam to miss the sail. Active stabilization, either through the beam shape or through small actuators on the sail, would be needed. There is also the question of what happens to the sail as it passes through the interstellar medium, the thingas and dust between the stars. Even at 20% of the speed of light, individual dust grains would impact the spacecraft with enormous energy, potentially causing damage. Challenge 3. Deceleration. This is perhaps the most fundamental problem. The laser beam from Earth can accelerate the spacecraft, but the acceleration phase ends when the spacecraft is too far away for the beam to maintain sufficient intensity. After that, the spacecraft continues at constant velocity. It has no way to slow down when it reaches Proxima Centauri. It will pass through the Proxima Centauri system at 20% of the speed of light. It will have only hours to observe the system as it flies through. Then it is gone, hurtling into interstellar space beyond. This is not necessarily a fatal objection for a first mission. You would still get a flyby of another stellar system. Data transmitted back would be extraordinary. But it is not the same as being able to explore a target system in depth. More advanced future missions would need to incorporate some form of deceleration. One idea is to toss a laser sail to break against the stellar wind irradiation of the destination star. Another idea is to carry a small laser with the spacecraft and use it to reflect laser light off the main sail, using thermometer exchange to slow down. These are complex and add mass to the spacecraft, which hurts the ability to accelerate it. There are also proposals using what are called magnetic sails or electric sails to break against the interstellar medium or the stellar wind of the target star. Challenge 4. Communication. Sending a signal from 20% of the speed of light, 4 light years away, using a gram scale transmitter and antenna, and having it received on Earth with enough signal-to-noise ratio to be useful, lies an enormous communication engineering challenge. The transmitter power available to a gram-scale spacecraft is tiny. The signal loss over 4 light years is enormous. Some proposals involve using a laser for the return communication as well, with the small spacecraft pointing a low-power laser back toward the Sun. Given the distances involved, even a tiny laser would spread out to cover an area billions of kilometers wide by the time it reached Earth, meaning the power arriving at Earth's detectors would be infinitesimal. With modern low-noise photon detectors and large receiving telescopes, this might be feasible, but it represents a significant engineering and operational challenge. Challenge 5. Timescales and funding. The total cost of the laser array and all supporting infrastructure is estimated to run into the tens of billions of dollars over many years of development. That is a significant, but not impossible sum for a global collaborative effort. The research phase funded by breakthrough initiatives is paying for the early-stage theoretical and experimental work to understand the feasibility of each component. Given the 20-year transit time plus development time, the first data from Proxima Centauri would likely not arrive until somewhere in the mid-21st century at the earliest, assuming development begins in earnest in the near future. Despite all these challenges, many scientists who have studied the concept believe it is fundamentally feasible. Not easy, not cheap, but within the reach of human technology in the 21st century. And importantly, the laser array concept has applications beyond just interstellar probes. A phase laser array of this scale could be used to rapidly accelerate conventional spacecraft within the solar system. You could push a crewed spacecraft toward Mars in days instead of months if you had a sufficiently powerful laser array. The infrastructure investment pays off in multiple ways. There is also a related concept called a laser thermal rocket, where the laser beam is not used for direct radiation pressure, but instead to heat a propellant carried on the spacecraft. The laser provides energy from a distance, and the spacecraft uses that energy to heat hydrogen or water vapor to very high temperatures and expel it as exhaust. This can achieve specific impulse values similar to nuclear thermal propulsion without the nuclear reactor on board. It is particularly attractive for launching payloads from the surface of other planets where you have a laser array in orbit. And then there are electron beam propulsion concepts, where instead of photons, you use a beam of electrons, which can carry more momentum per unit of energy under certain conditions. The physics is more complex, but the fundamental idea of energy transmitted from a distance to drive a spacecraft is the same. Let me also mention one more concept in the beam propulsion family: microwave thermal propulsion, sometimes called a beamed thermal rocket. In this concept, a powerful microwave transmitter on the ground or in orbit beams microwave energy to a spacecraft. The spacecraft has a microwave absorber that heats a propellant to high temperatures, producing thrust. Microwave beams are easier to produce at high power than laser beams, and some microwave frequencies can penetrate the atmosphere more efficiently. This could be useful for launch assist from Earth's surface, reducing the fuel needed for the initial climb through the atmosphere. Now I want to step back for a moment and give you the big picture of where all of this leaves us. We have talked about chemical rockets, ion thrusters, space elevators, nuclear thermal propulsion, nuclear electric propulsion, solar sails, electrodynamic tethers, magnetic sails, warp drives, and laser propulsion. That is a lot of concepts. Each one represents a different point on a spectrum from practical today to theoretical future. And together they paint a picture of a coming century in which space travel is going to look radically different from what it looks like today. Section 10. Fusion propulsion. The Holy Grail, Chapter 8. Fusion propulsion. The Holy Grail of space propulsion. If you have been following along, you might be wondering about something. We talked about nuclear fission, which is the splitting of heavy atomic nuclei like uranium to release energy. But we have not yet talked about nuclear fusion, which is the joining of light atomic nuclei like hydrogen to release energy. And fusion, in terms of energy per unit of mass, is even more powerful than fission. Fusion is the process that powers the sun. The sun converts hydrogen into helium through fusion, releasing energy at a rate of about 3.8 times 10 to the 26 watts. That is 380 trillion watts. Every second, for about 5 billion years, and counting. If we could harness fusion on Earth, or in space, the implications would be profound. And fusion propulsionis, arguably the most attractive propulsion concept, forapid, practical interplanetary, and even interstellar travel. Let me tell you about the physics first, and then we will talk about where the technology stands. The most practical fusion reaction for both power generation and propulsion involves deuterium and tritium, or DT fusion. Deuterium is an isotope of hydrogen with 1 proton and 1 neutron. Tritium is an isotope of hydrogen with 1 proton and 2 neutrons. When a deuterium nucleus and a tritium nucleus fuse, they produce a helium nucleus, a free neutron, and a large amount of energy. The energy released per unit of fuel mass is about 1 million times greater than the energy released by the best chemical propellants. 1 million times greater. That is not a typo. Nuclear fusion releases about 1 million times more energy per kilogram of fuel than burning chemical propellants. For a propulsion system, this means you could carry any fraction of the fuel mass and achieve far greater performance than any chemical rocket. The exhaust velocity of a fusion rocket would be enormous. Depending on the specific design, exhaust velocities of hundreds to thousands of kilometers per second are theoretically achievable. Compare that to the roughly 4 kilometers per second exhaust velocity of chemical rockets. You are looking at improvements of 2 to 3 orders of magnitude. With exhaust velocities of hundreds of kilometers per second, a fusion rocket could reach Pluto in weeks instead of years. A fusion rocket could reach 20 to 30% of the speed of light with a modest amount of fuel. Interstellar travel within decades, not millennia, becomes conceivable. So why are we not already using fusion propulsion? Because we have not yet achieved sustained, controlled fusion ignition on Earth, let alone in a form suitable for a propulsion system. This is the famous joke. Fusion power is always 40 years away and has been for 60 years. This is said with some bitterness by physicists who have been working on fusion for decades. But in 2022, something changed. The National Ignition Facility at Lawrence Livermore National Laboratory in California achieved fusion ignition for the first time. In their experiment, they used GOTA laser system to compress and heat a tiny pellet of deuterium and tritium fuel to conditions similar to the interior of the Sun. For the first time, the fusion reaction produced more energy than the laser energy delivered to the fuel. Fusion ignition. This was a landmark moment. Not because it means we are immediately close to fusion power plants. The laser system used to compress the fuel consumed far more energy than the fusion reaction released when you count all the inefficiencies. But it proved the fundamental physics of inertial confinement fusion, and it opened up a path toward future improvement. In parallel, many private fusion companies have emerged in the last decade, backed by billions of dollars in investment. Companies like Commonwealth Fusion Systems, Helion Energy, TAE Technologies, General Fusion, and others are all pursuing different approaches to controlled fusion. Some use magnetic confinement, like the classic tokamak design. Some use inertial confinement with lasers or other drivers. Some use more exotic approaches like field reverse configurations or plasma compression techniques. The diversity of approaches is actually encouraging. When multiple independent teams are pursuing the same goal with different methods, the probability of someone cracking the problem sooner rather than later increases. For propulsion specifically, there are designs that adapt the fusion concepts being developed for power generation. One particularly interesting design is the direct fusion drive, or DFD, being developed at Princeton Plasma Physics Laboratory. This is a compact fusion reactor design based on the Princeton field reverse configuration plasma concept. The DFD is designed not just to produce electrical power, but to directly produce thrust by allowing plasma to escape from their reactor and directing it with magnetic nozzles. The projected performance of the DFD, if it works as designed, would be genuinely revolutionary. Specific impulse values of 10,000 to 20,000 seconds, combined with kilowatts to megawatts of electrical power output and thrust levels of several newtons. For context, a few newtons of thrust with that level of efficiency would allow a mission to Pluto in about 4 years instead of the 9 years the New Horizons spacecraft took, while also delivering more useful payload. The DFD is still in the research phase. As of the early 2020s, Princeton has demonstrated the plasma physics of the field-reversed configuration approach and is working toward demonstrations of net energy gain from the fusion reactions. Another fusion propulsion concept is the fusion drive from MSNW, developed in collaboration with NASA. This design uses a technique called magnetized target fusion, where a magnetized plasma is compressed by a mechanical or electromagnetic driver to the point of fusion ignition. The fusion plasma fan expands and is expelled to provide thrust. The magnetohydrodynamic drive, or MHD drive, is another concept that uses magnetic fields to accelerate ionized plasma, potentially heated by fusion reactions, to high exhaust velocities. And then there is the Z-pinch fusion rocket, which we briefly mentioned in the nuclear propulsion section. A Z-pinch uses a large current pulse to compress a column of plasma, triggering fusion. The fusion energy heats additional propellant to extreme temperatures, and this hot propellant is directed out a nozzle. All of these concepts share a common theme. They are trying to use fusion reactions to heat and accelerate propellant to exhaust velocities far beyond what any chemical or fission system can achieve. The timeline for fusion propulsion is uncertain, but not pessimistic. If the private fusion sector succeeds in demonstrating net energy fusion in the next decade, and many credible observers believe this is possible, then the path from demonstrated fusion to fusion propulsion becomes much clearer. The physics is well understood, the engineering is enormously challenging, but fusion propulsion systems could potentially be operating by the middle of this century. Let me also mention the most extreme fusion propulsion concept, the Bussard ramjet, proposed by physicist Robert Bussard in 1960. The Bussard ramjet is an interstellar spacecraft that does not carry any fusion fuel. Instead, it scoops hydrogen from the interstellar medium, which, though extremely thin, is present everywhere in the galaxy, and uses it as both fuel and propellant in a fusion reactor. As the spacecraft accelerates, it scoops more and more hydrogen per unit time from the interstellar medium. The fusion reaction produces thrust. The spacecraft could, in principle, continue accelerating indefinitely, approaching the speed of light. Unfortunately, subsequent analysis showed that the Bussard ramjet faces some serious problems. The interstellar hydrogen is mostly normal hydrogen, not deuterium. Normal proton-proton fusion, which is what powers the Sun, requires conditions that are difficult to achieve in a practical reactor. The drag from scooping hydrogen actually exceeds the thrust from fusing it, at least with realistic scoop designs, which means the ramjet cannot actually accelerate. Some modified versions of the concept have been proposed, but none has fully resolved the fundamental drag problem. The Bussard ramjet remains a concept that is beautiful in imagination, but frustrated in its current physical analysis. So, fusion propulsion. The most potentially powerful near-term pathway to radical improvements in space travel. Fusion ignition has been achieved at NIF. Private companies are pouring billions into fusion development. Specific fusion propulsion concepts are being researched at major laboratories. The timeline is uncertain, but fusion propulsion is one of the most credible pathways to truly fast interplanetary travel within this century and interstellar probes within the next. Section 11, ANTIMATTER PROPULSION, the ULTIMATIMATTEROCKET, Chapter 9. Antimatter, the ultimate propellant. If fusion is the holy grail of propulsion, then antimatter is the philosopher's stone, the most energy-dense substance conceivable. Here is the physics. Every particle of matter has a corresponding antiparticle with the same mass but opposite charge. The antiparticle of the electron is the positron. The antiparticle of the proton is the antiproton. When a particle meets its antiparticle, they annihilate each other completely, converting all of their mass into energy via Einstein's E equals mc² dot all of their mass. Not 90%, not 99%, 100%. Compare this to chemical combustion, which converts about 1/10,000,000th of the mass of the fuel into energy, or nuclear fission, which converts about 0.1% of the mass, or nuclear fusion, which converts about 0.3 to 0.7% of the mass. Antimatter annihilation converts 100% of the mass of both the particle and antiparticle into energy. Per kilogram of antimatter, you get the maximum amount of energy that physics allows, about 9 × 10⁻16 joules per kilogram. That is about 90 quadrillion joules per kilogram. By comparison, the best chemical propellants release about 13 megajoules per kilogram. Antimatter releases about 7 billion times more energy per kilogram than chemical propellants, 7 billion times. With numbers like that, it becomes possible to conceive a spacecraft that can travel at a significant fraction of the speed of light. Some designs propose antimatter rockets that could reach 50 to 80% of the speed of light, making Proxima Centauri reachable in about 5 to 8 years of travel time. There are several proposed designs for antimatter rockets. The most straightforward is the antimatter-catalyzed nuclear pulse rocket, which uses tiny amounts of antimatter to trigger a fusion or fission reaction in a larger fuel mass. This reduces the amount of antimatter needed enormously. A pure antimatter rocket using proton-antiproton annihilation would produce a spray of pions, which are subatomic particles. These pions travel at about 80% of the speed of light and can be deflected by magnetic fields. In a concept called the Penning trap rocket, or the magnetic mirror antimatter rocket, the tapions are directed by magnetic fields to provide thrust. The specific impulse of such a system could theoretically reach into the millions of seconds. The problem with antimatter, and it is a massive, show-stopping problem, is making it. Antiprotons are produced in particle accelerators. You smash protons together at very high energies, and occasionally the collision produces a proton-antiproton pair along with other particles. Certain particle physics facilities produce antiprotons for research, but the efficiency is terrible. To produce 1 gram of antiprotons, you would need to run CERN's particle accelerators for millions of years. At current energy costs, that 1 gram of antiprotons would cost something like $62 trillion. And that is just the raw antiprotons. You still need to trap them, store them, handle them without letting them touch normal matter, and get them onto a spacecraft. Current total global production of antiprotons, IS, measured in nanograms per year. A nanogram, 1/1000th of a gram. We produce about 10 nanograms of antiprotons per year across all particle physics facilities worldwide. To fuel an antimatter rocket for an interstellar mission, you would need on the order of grams to kilograms of antimatter. The gap between current production and mission requirements is approximately 12 to 15 orders of magnitude. 12 to 15 orders of magnitude. That means we would need to be somewhere between 1 trillion and 1 quadrillion times more efficient at producing antimatter than we currently are. Is it conceivable that we could get there? In a very long time frame, potentially. A dedicated antimatter production infrastructure, perhaps powered by Addison sphere capturing a significant fraction of the sun's energy, could in principle produce meaningful quantities of antimatter. But we are talking about civilization-scale engineering, not near-term technology. For near-term applications, there is a somewhat more tractable version of antimatter propulsion. Antimatter-catalyzed microfission and fusion. In this approach, you use just a tiny amount of antiprotons, perhaps micrograms rather than grams, to initiate fission or fusion reactions in a larger mass of conventional nuclear fuel. The antiprotons catalyze the nuclear reaction, allowing it to begin at much lower densities and temperatures than would otherwise be needed. Because you are only using micrograms of antimatter, the production requirements are much more tractable. Micrograms of antiprotons might be producible within the next few decades with significant investment in production infrastructure. NASA's NIAC program, the NASA Innovative Advanced Concepts Program, has funded studies of antimatter catalyzed propulsion, and various university and national laboratory groups have published theoretical analyses of the concept. The bottom line on antimatter propulsion: the physics is impeccable. The performance would be extraordinary. The production of antimatter in useful quantities is currently beyond our ability by many orders of magnitude, and may require breakthrough advances in fundamental physics or civilization-scale energy infrastructure. It is not a near-term proposition, but as a long-term target for the distant future, antimatter propulsion represents the theoretical pinnacle of rocket propulsion, the end of the road for what you can achieve by throwing mass out the back of a spacecraft. Section 12, Other Frontiers, Reactionless Drives, DARKENERGY, and QUANTUMPROPULSION, Chapter 10, The Speculative Frontier. OK. We are now in territory where I need to be very clear about the difference between mainstream physics and highly speculative ideas. Everything from here on out is either highly controversial or purely theoretical, with no experimental support. But it is worth discussing because it illustrates where the human imagination is going in its quest to conquer space. Let us start with reactionless drives, also called propellantless drives, in a different sense from solar sails, because instead of using an external force like light, or the solar wind, These concepts claim to generate thrust internally, without ejecting any mass or interacting with any external field. The most famous example in recent years is the M drive. Proposed by British engineer Roger Scheuer in 2001, the M drive is a microwave cavity thruster. The basic concept is a tapered metal cavity that you pump with microwave radiation. Scheuer claimed that this device produced thrust without any reaction mass. The problem is obvious. This would violate Newton's third law and the conservation of momentum, which share among the most well-tested principles in all of physics. If momentum is conserved, you cannot generate thrust without ejecting mass in some form. Despite this fundamental objection, the EM driver received significant attention in the mid-2010s when several experimental groups, including researchers at NASA's EagleWorks laboratory, reported that they measured tiny but positive thrust from M drive test articles. The physics community was skeptical, and rightly so. Subsequent, more carefully controlled experiments showed that the apparent thrust in earlier tests was likely due to experimental artifacts. Thermal effects, electromagnetic interference with the measuring apparatus, buoyancy changes due to heating, and other systematic errors can produce spurious signals in very sensitive thrust measurement equipment. As of the early 2020s, the consensus in the physics community is that the M drive does not produce thrust beyond what can be explained by experimental artifacts. The measurements that initially looked promising have not held up under rigorous scrutiny. However, the story of the M drive illustrates something important. Scientists and engineers are still thinking creatively about alternative propulsion concepts, and the process of rigorously testing and debunking ideas is healthy. Some of those ideas will eventually pan out. There is a related concept called the Mach effect thruster, proposed by physicist James Woodward. Woodward's concept is based on an interpretation of fan effect in general relativity called Mach's principle, which relates the inertia of objects to the overall mass distribution of the universe. Woodward believes that it can exploit this effect to produce thrust by manipulating the inertia of a small capacitor using oscillating voltages and forces. Some experimenters have reported tiny, seemingly positive thrust signals from Mach effect devices. Unlike the M drive, the Mach effect thruster at least has a theoretical framework within general relativity, even though that framework is controversial and not accepted by most physicists. Testing of Mach effect thrusters has been funded by NASA and IAC and by various other sources. The results remain ambiguous and below what would be needed for any practical application. But the research continues. Then there is the concept of quantum vacuum propulsion. This is based on the idea of the quantum vacuum, the state of minimum energy in quantum field theory. The quantum vacuum is not empty. It seethes with virtual particle-antiparticle pairs, constantly popping in and out of existence. The Casimir effect, which we mentioned earlier in the context of exotic matter, is a measurable consequence of these quantum vacuum fluctuations. Some theorists have proposed that it might be possible to extract energy or momentum from the quantum vacuum to drive a spacecraft. This would be the ultimate free lunch, an infinite energy source distributed throughout all of space. Most physicists are extremely skeptical of this. The quantum vacuum is the ground state, the lowest possible energy state. Extracting energy from it would require going to an even lower energy state, which by definition is impossible. The Casimir effect, while real, does not provide a source of extractable energy. It is a force, like gravity, not an energy source you can tap. Nevertheless, there are fringe researchers who continue to investigate this area, and occasionally papers appear in journals claiming to have found a theoretical basis for vacuum energy propulsion. Let me also mention some even more speculative ideas that occasionally appear in physics discussions. There are theories suggesting that dark energy, the mysterious force responsible for the accelerating expansion of the universe, might somehow be harnessable for propulsion. Dark energy makes up about 68% of the total energy content of the universe, so if you could tap it, the implications would be extraordinary. But we do not currently have any theoretical framework for how to interact with dark energy in a controlled way. We observe its effects, the accelerating expansion of the universe, but we do not know its fundamental nature, and we have no idea how to produce or manipulate it. Dark energy propulsion is pure speculation. Similarly, some theories propose using extra dimensions of space, which appear in certain versions of string theory and M theory, as shortcuts or as ways to interact with physics not accessible in our four-dimensional spacetime. Kaluza-Klein towers, brane world scenarios, and other features of higher dimensional theories occasionally get recruited into speculative propulsion discussions. But the extra dimensions of string theory, if they exist, are compactified at the Planck scale, some 10 to the 35 meters. That is fantastically tiny. Interacting with extra dimensions at this scale would require energies far beyond anything conceivable. And then there is the concept of using gravity wave surgravitational fields for propulsion. Einstein's general relativity predicts gravitational waves, ripples in spacetime produced by accelerating masses. The LIGO and Virgo detectors have directly detected gravitational waves from merging black holes and neutron stars. Could gravitational waves be used for propulsion? In principle, radiation pressure from gravitational waves works just like radiation pressure from light. Gravitational waves carry energy and momentum. In practice, the coupling of gravitational waves to matter is extraordinarily weak. A gravitational wave from a merging pair of stellar mass black holes, which carries an enormous amount of energy, passes through the Earth with such a tiny effect that the distortion in space is smaller than the diameter of a proton. Gravitational wave propulsion, while not physically impossible in principle, would require gravitational wave sources of unimaginable power focused with precision that seems fantastically unrealistic. All right, I have taken you through the full spectrum of space propulsion concepts, from the chemical rockets that got us to the moon to the most speculative theoretical ideas at the boundaries of physics. Let me now bring it all together and give you the bigger picture. Section 13, The Big Picture, Humanity's Roadmap to THESTARS. Chapter 11, The Big Picture. We are living at an extraordinary moment in human history. For the first time, the question of whether humanity will become a multiplanetary species is not a matter of physics or technology. It is a matter of will, resources, and time. The physics and technology for getting to Mars are largely understood. SpaceX's Starship, combined with orbital refueling, can get there. Nuclear thermal propulsion can cut the trip time significantly. Once we're there, the resources exist to sustain a colony. The path to Mars is more engineering challenge than fundamental discovery. But beyond Mars, beyond the inner solar system, we enter a regime where we genuinely need new technologies. The outer solar system requires either very long mission times using current ion propulsion or faster systems like nuclear electric propulsion or fusion drives. And the stars require something more radical still. Let me give you a realistic roadmap of what the next 100 years might look like. In the near term, the next 10 to 20 years, we will see the maturation of electric propulsion systems. Hall thrusters and gridded ion thrusters will become standard for both commercial and scientific spacecraft. Solar electric propulsion will enable faster and more capable missions to the outer planets. Nuclear thermal propulsion may be demonstrated in space, enabling faster trips to the moon and making Mars missions shorter and safer. Laser propulsion experiments at small scales will test components of the breakthrough Starshot concept. In the midterm, 20 to 50 years from now, if fusion energy research bears fruit, which is increasingly plausible, we could see fusion power plants on Earth and the first conceptual designs for fusion propulsion systems. Space-based solar power and large-scale in-space manufacturing could enable the construction of laser arrays and other infrastructure that would be impractical to launch from Earth. The first serious proposals for sending crewed missions to the asteroid belt or to the moons of Jupiter and Saturn could be enabled by fusion propulsion or very powerful nuclear electric systems. In the longer term, 50 to 100 years and beyond, fusion propulsion could enable not just exploration but colonization of the outer solar system. The technology readiness of laser-driven interstellar probes like breakthrough Starshot's Starship concept could mature to the point where actual missions are launched. The first data from another stellar system might arrive within this century, and on a multi-generational timescale, the technologies that seem most speculative today, antimatter propulsion, exotic forms of nuclear pulse propulsion, possibly even hints of breakthroughs in physics that we cannot yet predict, might enable the ultimate ambition: humans traveling to other stars. I want to pause and say something that I think is important and often gets lost in these conversations. The stars are not our birthright. They are not guaranteed to be within reach. The universe does not away us access to its wonders. But we are the species that went from the first powered flight in 1903 to landing on the moon in 66 years. We are the species that developed quantum mechanics, figured out the structure of DNA, split the atom, sequenced the human genome, detected gravitational waves, imaged a black hole, and sent probes to every planet in the solar system. There is no law of physics that says we cannot develop the technology to reach the stars. There is no fundamental barrier that makes it impossible. There are enormous challenges. But enormous challenges have not stopped us before. The people who will solve these problems are alive right now. Some of them might be watching this video. The engineers who will develop fusion propulsion, the physicists who will figure out how to build a kilometer-scale phased laser array, the materials scientists who will create carbon nanotube fibers strong enough for a space elevator. These are real people doing real work. And what motivates them, what motivates all the researchers and engineers and dreamers in the space propulsion community, is the same thing that motivated every explorer, every scientist, every human being who has ever looked up at the stars and felt the pull of the unknown. We want to know what is out there. Section 14. The HUMANELEMENT. Why this matter? Chapter 12. The human element. Let us take a step back from the technology for a moment and talk about why this actually matters. Why should you care about ion thrusters and nuclear propulsion and laser sails? Why does any of this have anything to do with your life? Because it has everything to do with the long-term future of your species. Here is a perspective that I think does not get talked about enough in mainstream culture. Humanity right now is in an extraordinarily precarious position. We are a single-planet species. Every human being who has ever lived, every work of art ever created, every book ever written, every discovery ever made, every family, every community, every culture, every language, every song, every moment of beauty and joy and love that has ever existed on this planet, all of it resides on one small rock orbiting one ordinary star in an unremarkable corner of one galaxy among hundreds of billions. And that rock has, over the course of its history, been hit by asteroids. It has experienced supervolcanoes eruptions. It has suffered 5 mass extinction events that wiped out the majority of species alive at the time. And in the future, barring something extraordinary, it will be incinerated by our sun as it expands into a red giant in about 5 billion years. Putting aside cosmic timescales, there are more immediate risks. A large asteroid impact, which has happened many times in Earth's history, could cause an extinction-level event. A sufficiently large supervolcanic eruption could trigger a volcanic winter. Pandemic-scale disease, climate catastrophe, nuclear war, any number of scenarios could threaten human civilization or even humanity's existence. The philosopher Nick Bostrom and others have written extensively about existential risk, the probability that humanity might be destroyed or permanently disempowered by some catastrophe. Some of the most careful analyses suggest that the risk over the next century is not negligible. The obvious answer is to become a multi-planetary species. If humanity has populations on Earth, on Mars, in asteroid belt settlements, on the moons of Jupiter, no single catastrophe can eliminate us all. We become resilient. We become, in Elon Musk's phrase, multiplanetary and eventually interstellar. And here's the thing about space propulsion. It is the bottleneck. It is the single most important technical constraint on our ability to spread across the solar system and eventually reach other stars. Everything else, life support, radiation shielding, food production, water recycling, medical care in space. All of these are important engineering challenges. But they are fundamentally about making small, enclosed environments habitable for humans. We know a lot about how to do this. Propulsion is different. Propulsion determines whether the journey is feasible at all. A slow enough spacecraft is, not just an inconvenience. A 6-month trip to Mars creates health risks from radiation and muscle atrophy that need to be managed. A 100-year trip to Mars would be impossible for humans in any practical sense. Propulsion is the gating factor. And beyond the pragmatic argument, there is something deeper. Something that I think speaks to what it means to be human. We are a species of explorers. It is in our nature. It is written into our evolutionary history. Our ancestors crossed the land bridge from Asia to North America. They built boats and navigated the Pacific Ocean missing the stars and the currents. They climbed the highest mountains, dove to the deepest ocean floors, mapped every corner of the globe. The drive to explore, to see what is over the next horizon, to understand what is beyond the edge of the known, is not incidental to being human. It is central to it. The stars are the next horizon. They are the edge of the map. And for the first time in human history, we are developing the tools that might, within the next century or two, allow us to reach them. Think about that for a moment. Think about the billions of years of biological evolution that preceded humanity. Think about the millions of years of hominin evolution. Think about the 200,000 years of Homo sapiens. Think about the 10,000 years of civilization. And think about the tiny sliver of that history, the last 300 years or so, when we developed the scientific method, the Industrial Revolution, electricity, electronics, aviation, computing, spaceflight. We went from the first powered airplane to landing on the moon in 66 years. 66 years. If you were born in 1903, the year of the Wright brothers, you were still alive when Neil Armstrong stepped onto the lunar surface. The pace of technological change is accelerating. The resources being invested in space technology have never been higher. The number of brilliant people working on these problems has never been greater. We do not know exactly when we will achieve fusion propulsion or build a successful space elevator or send the first probe past another star. But the trajectory is clear. We are heading toward the stars. And that, I think, is one of the most extraordinary and hopeful things about being alive right now. Section 15. The INTERSTELLARMEDIUM and the CHALLENGESOF, Deep Space. Chapter 13. The interstellar medium and what lies between the stars. Before we get too dreamy about reaching other stars, let me bring you back to the hard physical realities of what the journey would actually involve. Because even if we solve the propulsion problem, even if we develop a laser sail or a fusion rocket that can get a probe to 20 or 30% of the speed of light, there are other challenges to confront. The space between the stars is not empty. It is incredibly thin by any Earth standard, but it is not nothing. The interstellar medium is made up of gas, primarily hydrogen and helium, and tiny solid particles called interstellar dust. The average density of the interstellar medium is about 1 atom per cc. For comparison, the air in the room you are sitting in right now has about 10 to the 19th atoms per cubic centimeter. So the interstellar medium is roughly 10 to the 19th times less dense than air. Incredibly thin. But at the speeds we are discussing for interstellar travel, even this incredibly thin medium becomes a problem. At 20% of the speed of light, every hydrogen atom in the path of the spacecraft hits the front of the craft with kinetic energy equivalent to that of a proton accelerated to about 6 million electron volts. In particle physics terms, that is in the range of cosmic ray energies. The spacecraft is effectively flying through a constant hail of cosmic ray-energy particles. Over the course of a 20-year journey to Proxima Centauri, A spacecraft traveling at 20% of the speed of light will sweep up a significant column of interstellar gas and dust. The atoms hitting the spacecraft will erode its surface. The radiation from cosmic rays and the interstellar medium will damage its electronics. The dust grains, even submicron scale particles, hitting at 20% of the speed of light will punch through any material with enormous energy, like miniature hypervelocity bullets. This is a serious engineering challenge for any interstellar spacecraft. You would need shielding. A solid shield at the front of the spacecraft would help protect it from gas and small dust particles, but a large enough dust grain could punch through any reasonable thickness of shielding. For the tiny Starship-type probe of Breakthrough Starshot, this is manageable to some degree because the cross-sectional area of the probe is tiny, just a few square centimeters, so the probability of hitting a problematic-sized dust grain during the journey is relatively low. Statistical analysis suggests that a probe with good shielding on the front face could survive the interstellar journey, though there is genuine uncertainty here. For a larger crewed spacecraft, the problem is worse because the cross-sectional area is larger, and you also need to protect the humans inside from radiation. One proposed solution is an active magnetic deflection system, similar to Earth's OWN magnetosphere, which deflects charged particles. But this does not help with neutral dust grains. Another consideration is relativistic effects. At 20% of the speed of light, time dilation is modest, but not negligible. From the perspective of someone on the spacecraft, less time would pass than from the perspective of someone on Earth. The difference is only a few percent at 20% of c, but it becomes significant at higher fractions of circa. At 90% of the speed of light, a journey that takes 10 years in Earth's reference frame would only feel like about 4.5 years to the travelers. At 99% of the speed of light, even larger time dilation effects occur. This is potentially useful for crewed missions to distant stars over very long distances, as it means the crew ages less than expected. But at the same time, communication becomes challenging. A spacecraft traveling at significant fractions of the speed of light experiences a Doppler shift in any signals it sends or receives. Radio signals sent from a spacecraft moving at 20% of CTO toward Earth arrive at Earth Doppler shifted toward higher frequencies and vice versa. The communication systems need to be designed to account for this. Navigation is another challenge. The nearest stars are relatively bright targets, but any planets orbiting those stars are far too faint to image from Earth. A spacecraft headed for Proxima Centauri needs to navigate to a precise point in space where Proxima Centauri will be when the spacecraft arrives, not where it appears to be now. This requires extremely precise knowledge of the star's position, proper motion, and distance, as well as onboard navigation capability to make corrections en route. GPS does not work in interstellar space. The spacecraft needs a method of self-navigation, probably using stellar observations combined with precise onboard clocks. At 20% of the speed of light, any error in the trajectory calculated at launch will be amplified over the 20-year journey. Mid-course corrections would need to be made based on onboard measurements, since communication delay to Earth and back would be 8 years at closest approach. And then there is the question of data return. What does the spacecraft see when it gets to Proxima Centauri? Proxima Centauri is a red dwarf star, much smaller and cooler than our Sun. It is known to have at least one planet in its habitable zone, Proxima Centauri. This is an extraordinarily interesting target. If the probe can image this planet as it flies past, even at low resolution, the data would be of immense scientific value. Transmitting that data back to Earth across 4 light years, using a transmitter that weighs about a gram and uses a few watts of power, is a monumental communication challenge. The signal arriving at Earth would be so weak that it would require the most sensitive radio telescopes on Earth to detect it. These challenges are real, but they are all engineering challenges, not fundamental physics barriers. Given sufficient time and resources, they can be overcome. Section 16, Astrobiology and the Motivation. Chapter 14, Why the Stars? The question of life beyond Earth. I want to spend a few minutes on the motivating question that underlies all of this. Why do we actually want to reach the stars? What would we hope to find? The most profound answer is simple. We want to know if we are alone. The question of whether life exists beyond Earth is arguably the deepest open question in science. It has been asked since ancient times. Philosophers, theologians, scientists, and ordinary people have wondered for centuries whether the stars in the sky are suns like our own, and whether those suns have worlds like ours, and whether those worlds have life. And now, for the first time in history, we have the tools to begin answering that question. The discovery of exoplanets, planets orbiting other stars, has transformed this question from philosophical speculation to empirical science. The Kepler Space Telescope, launched in 2009, discovered thousands of exoplanets by measuring the tiny dimming of a star as a planet passes in front of it. The Transiting Exoplanet Survey Satellite, or TESS, continued this work, and IS discovering thousands more. We now know that planets are extraordinarily common in the universe. The Milky Way probably has more planets than stars. There are estimated to be hundreds of billions of planets in our galaxy alone. And many of those planets are in the habitable zone of their star, the range of distances where liquid water could exist on the surface. Some estimates suggest that there are tens of billions of potentially habitable planets in the Milky Way. The discovery of Proxima Centauri b, a roughly Earth-mass planet in the habitable zone of the nearest star to our Sun, is especially significant. If there is life anywhere in the universe outside of Earth, Proxima Centauri b seems like one of the most likely candidates we are aware of. But we cannot tell from Earth whether Proxima Centauri b has life. We cannot even tell for certain whether it has an atmosphere. The tools of remote observation, even with the most powerful telescopes conceivable, have limits. To truly understand a planet, you need to get closer. A probe like Breakthrough Starshot's Starship, flying through the Proxima Centauri system, would have a brief but precious window of observation. Even a flyby at 20% of the speed of light would allow it to take images of Proxima Centauri b with much higher resolution than anything achievable from Earth. It could measure the planet's temperature, atmosphere, if it has one, even potentially detect signs of vegetation or other biological pigments in its reflected light, though this would be challenging. A more advanced mission, one that could slow down and enter orbit around Proxima Centauri b, could answer the question of life on that world definitively. With instruments that could directly sample and analyze the atmosphere, or it would transform our understanding of what life is, how it arises, how common it is, and what its future might be. It would have profound implications for philosophy, for religion, for our sense of place in the universe. And finding no life on Proxima Centauri b, or finding that it is uninhabitable, would also be important, though in a different way. It would tell us that Earth-like life does not appear in every seemingly suitable location, and that the question of why life arose on Earth remains even more mysterious. The search for life beyond Earth is not just a scientific curiosity. It is a foundational question about the nature of existence. Are we alone in this vast, ancient universe, this 13.8 billion-year-old cosmos, with hundreds of billions of galaxies, each containing hundreds of billions of stars? Or is life common, perhaps even ubiquitous? The answer, whatever it is, will change everything, and reaching it requires what we have been discussing all along: better propulsion. The ability to get there? Section 17, the PATHFORWARD, and What You Can Do. Chapter 15, The Path Forward. Let me bring this home. Let me talk about what actually needs to happen to turn the ideas in this video from dreams into reality. First, investment. Research and development in advanced propulsion requires sustained, long-term investment. Unlike many areas of technology where the commercial return on investment is clear and near-term, propulsion research often has payoffs on timescales of decades. This means it requires either government funding or visionary private investors willing to take long bets. The good news is that both of these are increasingly available. NASA's budget has increased in recent years. ESA and JAXA and ISRO and CNSA are all pursuing ambitious programs. And the private sector, with companies like SpaceX, Blue Origin, Rocket Lab, and many others, is investing at an unprecedented scale. The emerging fusion energy sector is also relevant there, because advances in fusion energy will directly feed into fusion propulsion. Private investment in fusion has reached multi-billion-dollar levels. If any of the current fusion approaches succeed, propulsion applications will follow. Second, talent. The people who will develop these technologies need to be educated, inspired, and supported. This means strong science and engineering education, particularly in physics, aerospace engineering, materials, science, and plasma physics. It means supporting researchers, giving them the resources and the freedom to pursue ambitious ideas, even ideas that might not pan out. If you are watching this and you are young, and you are interested in science or engineering, this is the most exciting time in history to be entering these fields. The problems are real, the stakes are high, and the opportunity to contribute to humanity's most ambitious project is genuinely open. Third, international cooperation. The challenges of interstellar travel are too large for any single nation. The laser array for breakthrough Starshot, the development of fusion power, the construction of a space elevator. If that becomes feasible, all of these will require global cooperation. The International Space Station, for all its political complications, demonstrated that humanity can cooperate in space when the will exists. The same spirit of cooperation needs to be extended to the most ambitious long-term projects. Fourth, public engagement and support. Public engagement with space exploration, when it is done well, generates enthusiasm and political support for investment. The images from the Hubble Space Telescope, the New Horizons flyby of Pluto, the landing of Perseverance on Mars, the first images from the James Webb Space Telescope, these moments captivate public attention and remind people why we do this. Videos like this one, conversations like the one you and I are having right now, are part of that process. Every person who understands the importance of space exploration and becomes an advocate for it contributes to the broader support that makes the work possible. And fifth, patience. The timelines for advanced propulsion technology are long. Nuclear thermal propulsion might be tested in space within the next decade. Fusion propulsion might be demonstrated in the second half of this century. Laser-propelled interstellar probes might be launched in the latter part of this century. Crewed missions to another star, if they ever happen, are probably at least a century or two away. This requires a kind of civilizational patience that is difficult for modern cultures, focused on quarterly earnings and electoral cycles. But humans have shown the ability to pursue multi-generational projects before. Cathedrals, the electrification of the world, the internet. These are projects that took decades to unfold. The stars require the same commitment, but on a longer timescale. And the payoff is incalculably greater. Section 18, the philosophical finale, chapter 16. A final thought. There is a photograph taken in 1990 by the Voyager 1 spacecraft. At the urging of Carl Sagan, NASA commanded Voyager 1, then about 6 billion kilometers from Earth, to turn its camera around and take one last look at home. What it captured is now one of the most famous photographs in history. Earth appears as a tiny pale blue dot, smaller than a pixel, suspended in a beam of sunlight against the vast darkness of space. Carl Sagan wrote about this image in his book Pale Blue Dot, and his words, which I will paraphrase rather than reproduce, spoke to the smallness of our planet, the insignificance of human divisions and conflicts when seen from that distance, and the responsibility we bear to be good stewards of this, the only home we have ever known. But there is another way to read that image, a complementary way. That tiny dot of pale blue light is not a symbol of insignificance. It is a symbol of potential, because everything that humanity has ever been and done and thought and created and hoped for has come from that tiny dot, and we are not content to stay there. We are not content to circle our small corner of one galaxy until the sun burns out. We want to understand the universe. We want to explore it. We want to find out if anyone else is out there. We want to carry life, the most extraordinary and improbable thing in the observable universe as far as we know, beyond the confines of this one pale blue dot. The propulsion technologies we have discussed tonight are not just engineering challenges. They are the mechanism by which life might spread beyond its original home for the first time in the history of the cosmos. Think about what that means. Life on Earth has existed for about 3.8 billion years. For all of that time, it has been confined to this one world. Every single living thing that has ever existed on this planet has lived and died here. No organism has ever survived to another star system. No piece of biology has ever established itself anywhere else in the cosmos. We might be the first life form anywhere in this galaxy or beyond to break that pattern, to carry life across the void. Or perhaps we are not the first. Perhaps, somewhere among the hundreds of billions of stars in this galaxy, some other civilization solved the propulsion problem before us and has already spread outward. Perhaps we are already surrounded by evidence of their presence, and we have not yet learned to look in the right way. Either possibility is extraordinary. Either we are alone in our drive to reach the stars, which makes our efforts all the more precious and meaningful, or we are not alone, and reaching the stars might mean meeting someone who has been out there far longer than us. I do not know which it is. Neither does anyone else. But I know this. The journey toward finding out begins now. It begins with chemical rockets and ion thrusters, and solar sails and nuclear drives and laser arrays. It begins with the work being done right now in laboratories and research centers and company headquarters around the world. And it begins with people like you, people who stay up late thinking about these things, who ask the big questions, who refuse to accept that the universe is too large and too distant to matter. The stars are very far away, but we are very stubborn. Section 19. All right, that was a deep one. If you have made it this far, first of all, thank you. This is exactly the kind of conversation I love having. And if you learned something tonight, if any of this changed how you think about space travel or the future or what is possible, then this video did what it was meant to do. Here is what I want you to do right now. Drop a comment down below. Tell me which propulsion concept blew your mind the most. Was it the laser sail that could reach another star in 20 years? The math behind why chemical rockets are fundamentally limited? The terrifying and beautiful idea of a warp drive? I read every comment, and I genuinely want to know what resonated. Hit that subscribe button if you are not already subscribed. We make these kinds of deep dive regularly, late-night rabbit holes into the biggest questions in science, technology, and the future. You do not want to miss what is coming. And share this video with one person who you think would appreciate it. Not spam it to everyone, just one person. That curious friend. That person who looks up at the night sky and wonders. Because conversations like this grow when people share them. The universe is big. But our curiosity is bigger. See you in the next one.